Fundamentals of E-beam Irradiation. STERIS Tech Talks are a series of webinars covering subjects relating to gas and radiation sterilization processing and the laboratory testing and validation services which support these processes. My name is Ashley Marute, and I'm the Associate Product Manager for STERIS Applied Sterilization Technologies, and I'll be the host for today's event. Our presenter today is Jonathan Jansson, a Principal Scientist at STERIS Applied Sterilization Technologies. John has 20 plus years experience in the radiation and sterilization processing industry, including E-beam, gamma, X-ray, EO, and moist heat sterilization modalities. John has supported STERIS AST radiation processing facilities in the Americas for about 5 years and has led a leadership role in a number of industry groups, including ASTM, We would like to encourage everyone to submit questions using the questions function on the GoToWebinar control panel. Questions will be answered following the presentation. Today's presentation will be recorded and uploaded to our STERIS Applied Sterilization Technologies YouTube channel. Please note that continuing education credits are not provided as part of this webinar. And now over to Jonathan to begin the presentation.
Hi, everyone. I'd like to start off with some terminology in relation to electron beam sterilization. And this is not a complete list, but first off, you will see quite a few times in this presentation the term MEV, which are the units for electron beam energy. This is short for millions of electron volts. The energy is the speed of the electrons. It's how fast the electrons are traveling. It determines the penetration ability of our electron beam source. And choice of the right energy is a key aspect of determining what you're going to be able to process with your machine. The milliamps of your beam are the amount of electrons produced by that beam. Larger beams typically produce higher currents or higher milliamps. The amount of milliamps directly determines the amount of speed that you're going to have to pass your product past your electron beam source to deliver a defined level of dose. Conveyance speed might be measured in any number of units. Typically at our sites, we're measuring in meters per minute, M per minute. It's this relationship that creates, with the beam, that creates the dose rate, and as consequences the time that the product is exposed to ionizing radiation. So for the gamma processes that we have, we think of a timer setting, which is the amount of time that a product will sit at a certain location being exposed to the source. The analogous attribute for an E-beam is conveyor speed. Conveyor speed is the primary way in which we control the dose delivered to products. Kilowatts, kW, is the irradiator power. It gives our throughput for our machine in a basic fashion. I'll go over that a bit more in this presentation. And a typical attribute of our beam that we often adjust for many machines is our scan length. You might call it the beam height, scan height. It can go by a lot of terms, but it's the dimension of the irradiation zone perpendicular to the direction of product movement. It's the direction in which we're scanning our beam. And it will determine also the amount of dose being delivered and consequently the speed at which we want to process our products. So some of the concepts that apply to the electron beam. First off, consider our electron beam machine to be somewhat similar to your old cathode ray TV tubes. Those old cathode ray TV tubes were an evacuated chamber with a heated filament at the back. That heated filament had current going through it, electrons would boil off, and those electrons were extracted with magnets off of their locality, and they were accelerated towards the glass screen that the viewer looks at. So our electron beams that we use for industrial sterilization operate in a similar fashion. We have a heated filament, electrons are boiled off of it, they're extracted and they're accelerated. But a difference is that our electrons in our processes don't simply hit the target window and activate phosphors and create light of different colors so you can see a picture. Rather, our electrons are accelerated at a much higher beam energy, and they're accelerated towards a thinner target. Our targets are metal windows that are there primarily just to contain the vacuum in which the electrons are accelerated. Those electrons penetrate that target window easily to go into the atmosphere and the region in our vault in which we are passing product through. So electrons are focused into a beam that scans across the product on the conveyor that is in our vault. So in its simplest term, the bombardment of material with high energy electrons creates this cascade of high energy electrons throughout our target material. Realize that our target material is full of electrons itself. It has a lot of atoms constructing molecules, and those molecules have lots of electrons in them. And when our electron source interacts with the target material, there's a cascade of electrons that are produced, and there's a dose distribution as a result. Products in our vault pass through this current of electrons to receive the required dose of radiation. And as mentioned, we control that dose through beam current, our beam conveyor speed, meters per minute, and our beam scanning length, which we're setting up to provide for the associated width or height of the product that is being processed. Okay, so a picture or two here, just to get you an idea. But what you see on the left here is an industrial electron beam. They come from a variety of manufacturers. The machine sizes vary greatly depending upon the power and the purpose. There's many machine designs with different modes of action to provide for high energy accelerated electrons. Users need to choose the machine design that suits their intended purpose. But a lot of our machines are rather large, like the one you see in this picture here. Some are a bit smaller. The picture on the right is just giving you some general concepts about radiation penetration. The top type of radiation there is the alpha particle. It's a helium nucleus. It can be emitted by certain radioactive isotopes. It's a very large charged particle consisting of 2 protons and 2 neutrons. Because it's large, because it's charged, because of its energy, it does not penetrate materials very well. You can see that there it's getting stopped by a sheet of paper. It's still hazardous to humans. I mean, if it gets in your lungs or mucous membranes through smoke or inhalation, it can damage and cause cancer potentially. Another type of radiation is the beta particle. We call them betas when they come off of radioactive isotopes. They are electrons. They have a negative charge. And we wouldn't typically use that term beta to describe a machine source electron radiation, but you could. I've heard the term beta beam. As you can see, that beta particle travels through your paper, but is blocked by something a bit more substantial, like a big chunk of wood. And those beta particles can certainly have a range of energies. Different isotopes would emit betas at different energies, characteristic energies of that decay process. And the beams, machine sources we use, emit electrons at a certain characteristic energy that we measure in terms of millions of electron volts. The other type of radiation that we typically use at STERIS sites or that we do use at STERIS sites, is gamma radiation. These are photons. They are massless. They're also emitted by radioactive isotopes. It's the same. It's the same as visible light. It's just at a different energy. Penetrates differently depending upon the energy of the. So our sources are typically cobalt-60 sources that provide for gamma radiation of products. Because of its nature, gamma radiation is highly penetrating. As you can see, it's stopped by multiple layers of concrete typically. For all of our processes, we have shielding that protects us from radiation. So as you can see, for an alpha particle, it certainly doesn't take a lot of shielding. A piece of paper can do it. And our processes don't use alphas. Alphas are present in laboratory environments for radioactive isotopes, but they're not something that we would use for industrial processing, whereas betas or electrons are, as are gammas that we use for sterilization purposes. So as far as shielding goes, you can see a cutaway of shielding here. We wouldn't normally ever be able to turn on a process that looks like what you see in this picture here. This picture has a cutaway of the shielding just so you can see inside. And you can see that the amount of shielding here might be sufficient for the type of source that we have. We have an electron accelerator in the upper right corner. This is just a theoretical diagram. I don't think we have a process that looks quite like this. But whether that shielding is substantial enough depends upon the energy of the beam that is creating our electrons. That's accelerating our electrons into our product. So as you can see from this picture, we have a certain flow through our acceleration of electrons process, or e-beam process. The product is flowing from the lower left through the process. It's a one-way path, and it's coming out again in the lower left. This process, as you see it here, is providing for one-sided irradiation, at least as far as what you see immediately visible. The product cartons are on trays there. Now, if you look in that lower left, there is actually a little transit zone that transits products from the input and the output conveyor. And this sort of feature can provide for two-sided irradiation. And the products would go through the process once. They'd go through that little transit, those two bars in the lower left, and they'd pass through the process a second time with the opposite side of the product load facing the electron beam. This sort of processing mechanism, two-sided irradiation, is typical for e-beam processes. It allows us to operate the beam at its highest energy and still and provide the best dose uniformity possible. And I'll explain that a little bit more in later slides. So considering these typical layouts we might have for electron beam processes, you see some potential layouts here. The first one that you're seeing is a two-sided process. It's a single pathway through the system to provide for two-sided irradiation by electrons. Pretty simple. You would need to control the conveyance speed above one beam and below the second beam to provide for the dose distribution that you're looking for in the products. So there's really two conveyors to control as far as speeds. Typically for a system like number one, we'd be very careful to set up the beams to be as symmetrical as possible. We want them to provide a symmetrical delivery of dose, similar in magnitude, similar in uniformity across the scan. System like number two, you see there's just a single beam irradiating from above. In that sort of process, there would typically be a transit on the outside, a rotate mechanism to provide for irradiation on a second side. This is not to say that you couldn't run your process as a single-sided process. Certainly some industries or some users will choose to do this, but you tend to sacrifice some of the uniformity of dose as a result. Number three is comparable to number two, except you're radiating from below. Number four is a horizontal beam arrangement from one-sided. We have a number of processes like number 4 in the Americas. This one's a floor-mounted conveyor type system. On the outside of the process, there would be a rotate mechanism to provide for two-sided irradiation. 5 is analogous to number 4, but it's an overhead conveyor. And 6, if you look closely on the right side, you'll see that there's a second beam hiding back there, so there's no rotate necessary for number 6. It's a single pathway through the process to provide for two-sided irradiation. Okay, so for some visual examples of these sorts of processes, you can see on the left, we have one of our sites. We have a picture here. This is actually a two-sided process. On the layouts, I can't remember the number now, but this is a top and bottom beam sort of setup where you see that top beam there. You see a carton going past. It's labeled tray conveyor system, but there isn't actually a tray visible in this picture. It can process lone boxes as you see there, or it can process a stack or arrangement of cartons on a tray. So it'll handle both arrangements. On the right, it does not, that carrier system, conveyor system does not require a separate tray. It consists of a kind of a tray conveyance system. What you see there is a setup for a horizontal beam arrangement. So in this case, the beam would irradiate the carriers from the horizontal side into the open walls of that carrier, of each one of those carriers. I'm not sure what site that is from. It doesn't look familiar to me. But that carrier system is not unlike some of those at some of our sites, for sure. And so that carrier conveyor system is very amenable to organizing products and any sort of arrangement you might want to provide the dose distribution that you're looking for your process. Another example here, this one looks like our Tullamore facility in Ireland. It's kind of a hybrid really in that it's a roller conveyor system, and typically the way they're using this is putting carriers on it. The carriers ride on the roller conveyor system and then products ride on the carriers. There is an input side on the left and output side on the right. What you're viewing here really is this outside area of the conveyance, and that element in the middle, I believe, is where there can be a pass-through. So that's that transit there where the product can go through a single pass and go back to the entrance to the input again and get irradiated on the opposite side of the load. So visually what that looks like here, you can see in this diagram, our product is getting irradiated on the one side. It's providing us with that pattern that we're seeing on the boxes. This is the sort of visual diagram you'd see on our control systems so that we understand in real time what loads, what carriers of product have seen single sides versus double sides. It's a useful visual tool in those systems. Going around for the second pass, you'll see products will end up with the coloring on both sides. You've seen both passes. The control systems are designed to ensure that every load of product sees the requisite number of passes and rotates. So the dose being delivered by electron beam is a function of our average beam current, our beam width, and our conveyor speed. You can see that relationship there. Dose equals K times I over V times width of beam. The dose of the product irradiated by an electron beam facility is proportional to the average beam current, or I, measured in milliamps, inversely proportional to conveyor speed and to beam width. So what you'll note about the equation when we talk about dose, the current is on the top half of the equation. That is to say, if we increase our beam current, we're going to increase the dose to our product. Everything else being the same about our process. Conversely, you'll see that the velocity, or conveyor speed V, is on the bottom half of the equation. We increase the velocity of our product passing past our electron beam, and the opposite effect is seen, our dose drops. Our residence time in front of the beam is reduced, the total dose drops. And similarly, the width of the beam has the same effect. So we increase the width of our beam, all other things being the same, our dose drops. So there's an inversely proportional relationship there. So our beam voltage, as mentioned, it's measured in millions of electron volts, or MeVs. Penetration electron depends upon the energy that the electrons have when they hit the product. Generally, we're operating our contract facilities at 10 MeV. And 10 MeV really is the point at which we need to, it's the borderline at which we would need to be concerned about potential impacts to some small amount of materials becoming radioactive, particularly metals. So if you go much over 10 MeV, you might find a small amount of induced radioactivity in some metals. It's really quite minor, but the normative standards have you assess for radioactivity if you're operating your electron beam anything over 10 million electron volts, which is why you'll see 10 million electron volts as the common energy of beams that we're trying to use for these sort of purposes. If we were able to and we wanted to operate the beams at higher energy to provide for higher uniformity of dose to products, we could certainly do that, but we need to make sure we cover the applicable parts of the standard regarding assessment of radioactivity. So that 10 MeV electrons will penetrate further than the 4.5 million electron volt electrons, very simply, and you can see that in this diagram here. I know there's little commas, so that's the European format for the numbers, but consider those as periods. So 1.5 million electron volts is our lowest energy electrons in this penetration diagram, or what we would call a dose depth curve. Now that x-axis, it's surface density. Consider that as fairly analogous to depth, penetration depth within a material in terms of centimeters. Grams per centimeter squared is just another way of looking at that same property. It's a density independent way of looking at that property. And so it's a common way to plot this sort of data. So what you're seeing here is as the electrons are accelerated at higher energies, they penetrate further. So going from that very top list on the right, 1.5, and you'll see a number of things going on there. So as the electrons are penetrating into the material, they're creating a cascade of electrons. And that cascade of electrons is resulting in increased dose with depth. And so that relative dose is peaking. It peaks earlier for those 1.5 million electron volt electrons. It peaks to a greater extent. But you'll see this family of curves has this characteristic shape. And this is something that we can't avoid. With all our expertise, this is physics. This is how the electrons distribute within our materials. Customers will come to us with certain needs for dose uniformity, but ultimately we'll be limited to what physics can provide for us in terms of the physical dimensions of the products and how those electrons scatter within the material and how dose builds up, as you see here in this diagram. The dose builds up with depth, and then at some point it peaks and it drops. And that's our continuous slowing down approximation range, that dropping area on the curve as it heads towards the x-axis there. So for beam power, we measure that in kilowatts. The power of an electron is measured by the number of electrons. The power of the beam is measured by the number of electrons it produces and the speed at which those electrons travel. So it's the multiple of our energy and our beam current we get our beam power. It's a pretty simple equation, so it's handy to point out here. So for a beam that's operating at 2 milliamps of beam current, operating at 10 millielectron volts, we have a 20 kilowatt beam. And I see a math error on that last line. That should be a 10 times 3.0, 30 kilowatts. So a really simple equation. A lot of our beams are operating in power ranges around 30 kilowatts. That is pretty typical. Some are operating at 15 kilowatts. Some systems have a number of beams in them, in which case we would add up the total powers to create the total power of the system. So if we have a 2-beam system at 30 kilowatts a beam, that would be a 60 kilowatt system. Electron beam dose distribution. So, and I've talked a little bit about this already, but once the customer has established the product irradiation dose range, they would do this. For one, on the lower end, for sterilization, it's the point at which we're effectively killing the microbes on the product. For any other purpose, we're looking for a low limit that is the minimum dose to achieve a desired effect within our product. At the upper limit, it still needs to leave the product in acceptable condition. The product needs to function correctly. So the manufacturer needs to assess their product for functionality. And that functionality depends upon the design of the product. There could be many attributes to functionality that need to be assessed during the product development process. To establish these dose ranges, a validation exercise must be performed on the same beam intended for routine processing. And I don't want to confuse it all. We need to establish the dose distribution within the product volume in the beam that we want to routinely process it in. And that is what we're calling our dose map of our product. It's our performance qualification of the product. We can't transfer that exercise from one beam to another. The dose profile within a radiation container is complex, owing to some of the things I've mentioned already, owing to this effect of change in dose with depth, complexity of the materials that we're putting into our process, the complexity of the mass distribution within the volume, the complexity of the materials, composition of the materials, voids, empty spaces, other things, other scattering elements within our process, such as the carriers themselves, which can scatter electrons. So we have a complex dose distribution. It's also due to the presence of secondary electrons being scattered, being built up within the product. Max dose location is not usually on the outside of the product. Gamma, that might well be a reasonable thing to state, but not for electron beam. So for electron beam, you saw that increase in dose with depth. Typically, max doses are within the volume, but not always. And to understand where the dose is, max and min, we need to do this study of the dose distribution. In comparison to gamma, our max-min ratios are often a bit wider for E-beam than for gamma. Typically, we want to provide for higher maximum doses for electron beam product. That's not to say that electron beam sterilized product will be more affected as compared to gamma. Electron beam processed product oftentimes is less detrimentally affected by the radiation due to the nature of the process. The electron beam process is quick. It delivers the dose in a short amount of time. There's a short temperature profile that the products see through the electron beam process. So the process occurs in the space of minutes as opposed to hours. That can occur for gamma. So we'll need a comprehensive dosimetric validation to gain the true picture of the dose distribution in the volume. Now, I talked about two-sided processes. Here's the diagram to get you an idea of what that might do. Here we have our theoretical carton of product. We're going to hit it on both sides with radiation or electrons. Those are our little green squiggles there on their left and right sides. And for this particular product, in this case, of this density, and it's pretty uniform, we get a nice dose profile. We get this depth dose plot, like you see here. What you see is a reasonable representation of it. And we're getting certainly past the middle of the depth of the product in this particular situation. So that looks pretty good. We irradiate on the second side, and we get that second profile that you see there. It's the mirror image. And we say, okay, well, it looks like the dose might be a little low in the middle, but realize that when you combine the two curves, you get that black curve that you see at the top. And our DUR really is that max to min ratio for this type of configuration. And it looks like at the very edge on the left and right side, perhaps is about halfway up the chart. And in the middle, it peaks to maybe 3/4 of the way up the chart. So the dose uniformity ratio would be our max over our min, which would be those points on that y-axis, that 3/4 point over the half point. And that would effectively determine the dose uniformity in this particular product. And this is a very idealized situation, and it's actually a pretty good setup because the way these two curves are combining, it's providing a little bit of dose depth, a dip in the middle, but not too much. And so we're not getting a min dose in the middle. We're getting some sort of medium or middle dose in the middle, and peaks where we might expect them to be. But this ideal case isn't necessarily what might occur for any given product, and is why we need to study and perform our performance qualification dose mapping exercise to understand the true dose distribution of the product. So if we increase the density of our product, or if we increase the thickness of the product we're trying to penetrate, we have the same sort of situation here. We're going to hit it from one side with the electron beam. We can hit it from the opposite side with our electron beam. And our total dose is going to combine. And in that middle, it's not going to be that good. In fact, we'll probably get a zero dose in the middle, which would be an example of why we definitely want to place dosimeters throughout the product volume to understand where the maxes or mins are within that volume. That min dose could be in the middle. It could be a zero dose. In that case, there would need to be changes in our product configuration by some means, or some change to our electron beam. It could be an energy increase that would make our electrons penetrate deeper. And there might be other changes that we can affect, which is really one of the really neat things about processing with electron beam, is that from the user side, we can change our products, but we can also change our source to suit our particular needs in a given circumstance. So as far as applications that we can use our electron beam in, you see some examples here. Electron beam is very successful for low to medium density products that are homogeneous: gauze, drapes, towels, bandages, wound care dressings, lab work, things you see here. Things are, with these types of products, we have similarity of a small or a few number of materials, a nice mass distribution within the volume typically, not too many very high density components. This is not to say that electron beam won't work perfectly great for some very complex stuff, but we need to be careful with it. We need to make sure that it will meet the needs for that particular process early on. We don't want customers to spend inordinate amount of time setting up for very complex products under the hope that they can be e-beam sterilized. This sort of thing needs to be looked at early on in the product development process. So as far as how we might configure products for electron beam, here are some considerations. Shadowing and scattering effective E-beam radiation can be very significant. Dose distribution inside the container would be significantly affected by the orientation of the product in the box, orientation of the box in the conveyor or carrier system, change in the carrier density. You can see two possible radiation configurations for, very simply here, a set of product units within a carton, irradiated from two sides. You have two basic options being depicted here for orientation of that carton to the beam. And in this case, yes, our DUR is a whole lot better, that one on the right. Now you're penetrating a deeper depth, but in this case, it tended to work out better. And that could be, oftentimes that might occur due to the mass distribution as viewed on the surface. Think as if you did an X-ray, like a human X-ray, but now you're X-raying your box carton, and looked at that picture to see where the high density and low density areas were from that one-dimensional view. And if you have a more uniform picture, then you should overall get a better DUR in a given dimension as compared to that X-ray picture in the other direction. For a product like what you might see there on the left, you can see that it's got some rather sharp mass gradients to the volume. You have a very a dense black handle in the upper right of that product on the left. You have a kind of a tube or a cord there wrapped in circles that's got a certain density to it. Now, from the manufacturer side, how that product is arranged within the carton, that carton plan for E-beam radiation, will matter greatly to what the DUR is. As you might be able to picture, there's a number of ways you could orient that product in the carton, and how those product units might stack. Now, if all those handles are all stacked in a row and you radiate through that stack, you're trying to penetrate a very dense area of the product. And that really dense area is really going to drive what your total dose uniformity within your volume is. So considering these two diagrams on the bottom, that one on the left, you're penetrating, looks like 9 units. That one on the right, you're penetrating 2 units, left and right. So oftentimes trying to penetrate fewer units can lead to better DUR results like you see there. So considering the materials construction of various products, here are just some pictures for examples to augment the discussion that I had on the other slide. So these, like at the top, you see 1, 2, and 3. There are a few materials of construction here. The Petri dishes, they're all constructed from the same plastic. This is relatively homogeneous material. This is not to say that it'll get the best DUR because it's a rather large box. But it should be a fairly homogeneous dose distribution throughout the volume because you see the same pattern repeat. And overall, you just have air and one type of plastic. Number 2, looks like some plasma pooling bottles, fairly simple as well. Number 3, some sample cups, and a random arrangement to point out there, which makes it a bit harder to dose map because it's hard to have a repeatable configuration of the product. But it's fairly simple there. It's low density. It should provide you very good DUR. 4 is a bit of an unknown. And to that point, for our studies, we need to open up all the product cartons. We need to make it very clear within the studies what we are characterizing the dose distribution to, so it can be supportable of a certain product validation on one of our systems. We need to be clear on where we placed all the dosimeters, how the product was received, how it is configured within the volume. Number 5, that example from the prior slide, it's certainly got some high mass areas. Might work fine for E-beam, but this is the sort of product that you definitely want to be a little bit more careful of in establishing the max and min dose, because the wrong type of configuration could provide you certainly too wide a dose distribution. That won't meet the customer specs. 6 is simply a complex sort of kit. So there's a lot going on in number 6. The point there is there's a lot of dosimeters you might be placing in that volume. The more complexity to the volume, more types of materials, the more components, typically the more intense dose mapping is, the more product units per volume as well can certainly affect that. So some considerations for PQ. Not every product will have an ideal orientation. Some max-min ratios will be greater than 2 to 1. Products will have a variety of densities, exhibit a wide max-min ratio. These can tend to be difficult to dose map. E-beam processing may require more dose mapping than gamma or X-ray. In fact, that's almost always the case. We're typically expending more effort to characterize dose distribution to E-beam process products. There's typically more work up front. We can establish processing categories for E-beam, but we need to be careful about that. We need to have within that processing category similar product, dose specifications, packaging loading patterns are the same. So they can be established, but we need to carefully evaluate the products. And we would commonly dose map a number of products within a category to establish it. And the results of those maps would be combined as far as the correlation ratios between the reference location and the product dose, because E-beam processed product is routinely monitored at a reference location. There's not typically an option to monitor dose on the product itself or to directly monitor dose to products, because to place the dosimeters in the products, you would compromise those products. So E-beam processes, what you'll see is a reference location dosimeter, and that's part of the purpose of that dose mapping exercise, is to establish the relationship between the reference position and the dose to the product itself. We change anything about the product orientation, the configuration of the system, we change the E-beam itself and how it delivers the dose. We're going to need to repeat that PQ. Dose mapping is a destructive test, but we'll conduct that dose mapping on dunnage units. They need to be physically representative of the routine product. And those dunnage units could serve as dunnage filler and routine processing. So some comparisons between different industrial irradiation processes. You can see some details here. E-beam in the middle. Temperatures can be a little higher. Process is quick. Dose ranges are wider for E-beam compared to gamma or X-ray. And that's due to the nature of electrons penetrating material. They're charged particles. They have a mass and they distribute dose. As a result, that's a bit wider than gamma. And X-ray are the same as gamma. Effectively, they're photons. So they're massless, chargeless radiation. Okay, well, that wraps up the main content of my presentation. I'll turn it back over to Ashley.
Thanks again for joining us today, and this concludes the webinar.